Hello students, welcome to AcadShala.
Let's roll on with 3R series, that is recall, revise, retrieve. Today we are going to do part 8 of chapter 13, magnetic effects of electric current.
But before starting today's session, it would be great if you like this video, share this video and subscribe to our channel AcadShala. This gives us a lot of motivation to keep creating these kind of videos for you all.
Students, today in this session, we are going to do one question which is very important. You need to know the concepts and then utilize in the question very well to solve it. So the question says, a coil of insulated wire is connected to a galvanometer. So that means over here, we have taken an insulated wire which is connected with a galvanometer. And students, before that, you should know what do you mean by a galvanometer? Galvanometer detects the current in a circuit. Now there's a needle also in the galvanometer which detects the current. It moves left or right, or in the middle it stays. And if it stays in the middle, it indicates there is no flow of current. If there is a deflection towards left or right, that means there is a current in it. Okay. What would be seen if a bar magnet with its south pole towards one face of the coil is moved quickly towards it, moved quickly away from it, placed near its one face? Before starting this, first of all in the question, you need to understand the meaning of phase. It is nothing but ends of the circuit. So students, do not get confused if it comes in the question phase, because in the daily language we use the word ends of the circuit. So if the phase comes, meaning it is ends only. So meaning is same for both the words, phase or ends. Okay, now if you see in the diagram, children, that there is no circuit diagram given in the in the question, but for solving the question, we need to make the diagram on our own also, so that we can solve the question in a very well-versed manner. So for this, I have made the diagram over here, which is shown in front of you on the screen. So what I have done, according to the demand in the question, I have taken an insulated wire and then I have connected the wire with the help of a galvanometer. And these are the ends or the face. Okay, children? And the galvanometer also has a needle which shows the deflection towards left or right according to the induced current. And if it shows in the middle, it means there is no current. Okay, children? So we have made the diagram to satisfy the question as shown over here. And we have connected with galvanometer also according to the demand in the question. Now children, you know it as I told you earlier that this coil has two ends, that is face or ends, and there is no problem if we know that these are the ends or the face. We will not get confused at all. Now children, we have a bar magnet also which has two, that is what? South and north pole. Okay, so what I have taken? This bar magnet and I have moved this bar magnet according to the first, this part of the question. I have moved the bar magnet, that is, I am moving quickly towards it like this. I am moving it continuously. I am not leaving it. That means I have to move the bar magnet quickly towards it. I will not do this work in a slow motion or in a very slow manner. I will rather move the magnet very quickly towards it. So after I move towards towards the face of this circuit, I see there is a deflection. And when I move it away, that is quickly move away from the circuit, I again see the deflection. And when I only keep the magnet very close to the face, I see there is no deflection. I see the needle always in the middle if I Only place close to the face and leave it for some time. There is no deflection in the galvanometer. That means no current is flowing. So with this, we have come to know the first thing that we have to keep on moving the bar magnet. We cannot make it still or very slow so that magnetic field is produced. And if magnetic field is produced, so what is there? Induced current is also there. So always remember, children, what is the demand in the question and what you have to do it. Okay, now after we know that if there is a deflection, that means there is induced current, there is a flow of current. Now, children, you should also know that when the magnet is moved quickly towards it, it moves in the left-hand side. What? Needle of the galvanometer. So that means it is clockwise. And if we move the bar magnet, that is quickly away from the end or the face, what happens? Deflection will be seen towards right and it is anti-clockwise. And when we keep the bar magnet close to the face or the end of the circuit, there is no deflection. So the needle is shown always in the middle. So this is what you need to understand, children, very, very well. Now, overall, the concept, you should also know it that magnets, that is the magnet's magnetic field. I repeat, magnetic field, which is associated with the coil. I repeat, magnet's magnetic field, which is associated with coil, that will change in respect to the coil when magnet is moving closer or away. Then magnetic field will change and hence current is induced, which is called as EMI. It is not the EMI of your house and all. It is known as electromagnetic induction, which is really very, very important to note. And when magnet is just kept closer to the end or the face of the circuit, there will be no deflection in the galvanometer, hence no current is induced. So, if you have understood the language of the question of these three subparts of the question, we have made according to this the diagram, we have understood the concept, we have utilized, and now we will learn how to solve the answer that is of this question. So how to write it, that also you will understand. So in the first part of this question, so a coil of insulated wire is connected to galvanometer, and if a bar magnet with its south pole towards one face of the coil is moved quickly towards it, the galvanometer is deflected towards the left, which I told you. That means what? Clockwise. And always remember that we have kept the bar magnet with its south pole. Okay, children? So the second part says, moved quickly away from it, the galvanometer is deflected towards the right, that is anti-clockwise. If the magnet is held stationary inside the coil, the deflection of the galvanometer is zero as no change in flux. So no deflection, needle in the middle will be seen. And the diagram which we have made it on our own, that is, this is the way the diagram is also shown. The ends or the, what children? Face, which I told you. So this is A, face or end. This is B, face or end. And in front or close to it, the bar magnet was kept. That is facing south pole towards it. And the whole of the picture which I have discussed and explained you very well, it is going like this. When we place the magnet, bar magnet facing south pole towards one end of the face or end. End or face meaning is the same. Okay, children? So let's go further. Now, on coil B, that is the part which is known as the end or the face, which is known as B, that means on coil B face, closer to it we are keeping north pole of bar magnet. Now what we are doing? So that means in this activity, we have to repeat with the north pole of the magnet. In the earlier activity, we were doing with the south pole of the bar magnet. That means it was facing towards this side, the south pole of the bar magnet. Now the same activity will be repeated, but the only difference will be that now the north pole of the bar magnet is near the end of this coil. Okay, children. Now we are keeping north pole of the bar magnet very close. That means we are moving. That means the north pole of the bar magnet towards the end or towards the face of the coil. And the magnet's magnetic field, which is associated with coil, that will change. Yes, children, in respect to coil. When magnet is moving closer or away, then magnetic field will change and hence current is induced. So hence there will be a change or deflection in the galvanometer as you are watching, children, on the screen, and the deflection will tell that when the north pole of the bar magnet is moving towards the face or the end of the coil, what will happen? Deflection in galvanometer will be there and the deflection will be shown towards right over here. As you're seeing it, in the previous it was left and over here it is towards right. And when the north pole of the, bar magnet is moving away, that means moving where? Away from where? Away from the coil. That means this end. So what will happen? So the deflection in the galvanometer will be seen towards left over here like this, towards left. And now what happens if we only place the bar magnet, that is the north pole of the bar magnet, only near the end or what? End or the face of the coil, we will see the deflection in the galvanometer in the middle only. Yes or no, children? So you have come to know that in the first, second and third cases, we have seen the deflection in the galvanometer when the bar magnet is going closer towards, but always keep it in mind that it is moving quickly. Yes, children. So the deflection is towards right. Another case when it is moving away from it, so it is towards left. And when it is not moving, only it is permanently there near the face or the end. So the galvanometer is showing only in the middle straight needle, showing there is no deflection, no current is induced. Am I clear, children? So this is very, very clear about it. That is when the activity is repeated with the north pole of the magnet. So it will be opposite of what we did in the previous activity. Okay, so the next thing is the B part says the question was name and define the phenomenon involved in above activities. Of course, whatever I've told you in detail, again the same thing, that is the phenomenon involved in this activity is electromagnetic induction, which I told you earlier also in some part of the question. So it is a process in which current is produced because of voltage production. So that means current is produced. Why? Because of the voltage production, which is known as electromotive force, and due to the changing magnetic field. And how the magnetic field is changing? That means we are moving the bar magnet to and fro, and that is why we are changing, and then the magnetic field is also induced, hence current is induced. Finished. Yes, children? So this is very, very important. So the last part over here is name the rule which can determine the direction of current in each case. Okay, children, over here it is very, very important, and it is a minute point to be, you have to understand the concept that, as I told you, I'm talking about on and on about electromagnetic induction. Yes. So we have studied also that in electromagnetic induction, when we have to find induced current direction, I repeat, in electromagnetic induction, when we have to find induced current direction, so we use which rule? Which is known as Fleming's right hand rule. Am I clear, children? So what happens that in some of the question, as it is given over here, that is somewhere it is also written the induced current, children. Sometimes it is given induced current also. So do not get confused. They're talking about electromagnetic induction, and that in electromagnetic induction, when we have to find the induced current direction, we use which rule? That is the Fleming's right hand rule. This finishes this question, which comprises of many concepts pouring in to solve in the best possible manner. And of course, when you solve the question stepwise with your concepts which were clear to you when you studied this chapter earlier, will make this question absolutely correct with full marks. So with this, the session ends, children, today. So please keep on revising your concepts very nicely and you will do wonders in your exam. So with this, I wind up the session. Bye-bye. God bless. Take care.